Good day, everyone. Welcome to this module, the introduction of well engineering. In this module, we'll be jumping straight into discussing how data is gathered, how a well engineer designs his well and executes his well safely in an efficient and optimized manner. We'll be talking about everything a drilling engineer should know, from bit selection to casing design to trajectory design to kick tolerance. We'll be looking at the whole details. So this is the first of the videos in the series, and we'll be introducing the roles of the drill engineer. So as we go ahead to jump into the topic, do not forget to share, do not forget to like, do not forget to subscribe, and turn on the notification button so that you can know when we up in new videos with regards to this model. So moving right straight into it, we will go ahead to this is the outline. We'll go ahead to introduce the topic, talk about the responsibilities of a drill engineer, and look at the well development process. So look talking about the well development process, which is like 90% of what this presentation is about. It looks at the whole details, what a drill engineer puts on the table, what he looks out for, and what he looks at when designing the well. Pretty much the whole process from top to bottom. So, who is a drill engineer? Looking at it, reading it verbatim from what we've written here, I would say a drill engineer specializes in the design, planning, and execution of drilling operations. So, keywords: he designs the well, makes necessary plans, and he goes ahead to monitor the execution of the drilling operations. So, there's a lot of detail that goes into the design. There's a lot of detail that goes into the planning, and of course, he needs to always be on his toes during the operations to ensure that what he has designed is the way the well will be executed. So those are the roles pretty much of a drill engineer. And why is he doing all this? It's for the purpose of extracting oil and gas from the reservoir up to the surface. So who is a drill engineer? I just threw this up here so that we see that a drill engineer is doesn't work in isolation. He's embedded into a team that comprises a whole lot of people. To the side here, we see the sedimentologist that tells us pretty much which sediment, what clastics, that's if it's in a classical environment, or I mean, if it's a carbonate environment, what kind of reservoir do we have? We have the geophysicist looking somewhere here, we have the geologist here, we have the geoscientist, we have the petrophysicist, we have the production engineer, the reservoir engineer, the computer engineer who works closely with the drill engineer to ensure that these wells are properly planned and are able to get hydrocarbons to surface. So you see, these are the group of people that he works with to ensure that we that these wells are. I mean, wherever this hydrocarbon has been mapped, that we go there and confirm, because that's pretty much our job. We go there to confirm that yes, the hydrocarbon that they say is there is actually there, and we drill it, get to where they are, and plumb them up to surface. So that's pretty much the role of a drill engineer. So, what are our responsibilities? We, like I mentioned in the other slide, we plan and we design and plan the well. We monitor the operations where the well is being drilled. We coordinate the project from top to bottom, working with a lot of people. Like I showed on the other slide, we're working with the geophysicists, the geoscientists, the sedimentologists, the geologists, the completions, a whole, I mean, lots of people to ensure that our goal of getting the hydrocarbons to surface is successful. We monitor the performance because I mean we select them going back up there, we select the equipment, ensuring that whatever hydrocarbons that we are getting up to surface, that the equipment that we've chosen for that in no way does it adversely affect the equipment that we've chosen. We monitor the performance. We don't want to drill wells forever. We want to be sure that whatever well we are drilling is drilled in record time, and whatever hydrocarbons we are getting up to surface can actually pay for that well and put profits in our pockets. That's actually why these wells are drilled. We don't want to drill wells that at the end of the day it records a loss for the company or the client. Drilling engineer will be looking at well control. We'll be talking about that extensively. Of course, cost management to ensure that the equipment that we are taking out to the rig to drill these wells, after they are being used, they are taken back to base. If they're rental equipment, if the equipment that we don't need to use, they are returned back to the contractor. If the equipment that are excess, we plan them that extra equipment from the well that we drilled. If it's a campaign, they are used for future wells. Of course, safety is very important. We want to be able to drill these wells without hurting anybody. Problem solving is a, a big skill that a drill engineer should have, because yes, we make plans, yes, we make designs. We these wells are properly designed. We plan effectively. We write an operations drilling program, but things don't always happen the way we plan them. There will be issues. There will definitely be issues. So you need to be, that's where the thinking cap of you as an engineer comes up. You're able you that's where you put out your problem solving skills. You're able to brainstorm, mind map, put everything you're seeing that is happening at that time on the table and come out with a solution. That should be one of the main skills, one of the major skills of a drilling engineer. So, looking quickly, this is what the well delivery process looks like. Talking about it from top to bottom, you have to acquire data, and after that data is acquired, to be thoroughly reviewed. So part of the data you're going to be getting the well data sheet from the subsurface team. There will be a lot of offset data, perhaps not from that field, but from surrounding wells in that field. There need to be some area experience so that you know where you might have wellbore stability issues, where perhaps it's highly pressured, or perhaps that area is being produced, it's becoming a brown field. You're having low pressures, a lot of compaction, and the wellbore stability and also wellbore stability issues. You have to have area reference data that when you are planning the well, you are putting all those risks that have been identified in that area into your well plan, ensuring that you are designing this well and you are factoring in everything. That's what pretty much what the area experience is speaking about. You are designing the world and you're putting in all the area experience from that environment into your design, so that when your team comes out there drilling those wells, they're putting all those things. You've kind of advised them. For example, in a particular depth, you're expected to have losses. You've advised them that, hey, at this depth, well, A, B, C, D saw losses. So once you're getting to that depth, you're already treating the mud with low circulating materials, ensuring that it plug up the voggy areas or the high permeability areas, ensuring that you have no losses. Well, so you are taking the area experience and you're building it into your operational plan, ensuring that the things that happen in the past wells don't happen to you and you drill these wells efficiently. After you have acquired and reviewed that data, you are analyzing data, taking all the lessons, taking all the whole section summaries, taking all the contractor reports. What are the things that you can learn from? Because you don't want to come on a new well and relearn a lesson that's been learnt before. That will really make you a very bad engineer. You want to be able to read all the reports, get all the information, take all that information and put it into the new design. That way, you curb a lot of risk, and of course, you'll be drilling a very efficient and an optimized well. Um, After you have all that data, the first step is looking at the concept of how that well will be drilled. And after you look at the concept, you outline various concepts that it's possible that, the way that well can be drilled, then it is brought to the table. So you'll be looking at just not just the drilling, but you're also looking at the completions, which is the plumbing, getting the hydrocarbons to surface. And once the concept is reviewed and agreed by the team, then you go ahead to design the well. Once the well is designed, it will be peer reviewed. So you have designed the well as an engineer. Others will be looking at it. They'll be looking at it with the second pair of eyes. Perhaps there could be places where a couple of things could be changed or optimized and made better. And after that is done, the design will be reviewed or updated. Then you can move ahead into well programming. And as we are programming the well, that is how the well will be executed, how the well will be drilled. So well programming is pretty much the document that comes out of it is the drilling program. And as you are programming the well, we're also looking at the possible risks. So going to drill the top hole section, what are the risks? Okay, we can have losses, you can have stock pipe, you can have shallow gas. Those are the risks. How do you curb them? So you are looking at the possible risk, and you're analyzing and putting mitigations in place. And they'll also be there as part of your, they'll be written in the program, because there'll be steps on how each of these risks will be mitigated. Then after that is done, we have a well program and risk analysis review, ensuring that we've captured everything that all the possible risks in that environment, that we're not missing out on anything, and that all the steps of the program are exhaustive. Then finally, we'll have the drill well on paper that's had on shore, where you bring all the members of the team, the contractors, the rig contractors, the service contractors, everybody sits down to look at the design and the operations program in total, where they look at everything, anything that is being missed out. I mean, everything is looked at. So the well is drilled pretty much on paper. Everything is reviewed, ensure that all the required steps are captured, all the equipment are looked at. Members of the team ensure that they understand how the well is expected to be drilled. Then another meeting will be held in the field. That's the pre-spot meeting. That's the last one that will be held offshore. So it's similar to the drill well on paper that is had onshore. However, the pre-spot meeting is had by the core member of the team that will be on the rig discussing, ensuring that they understand their rules before the well is being executed or before the well is spotted. So I just put up this up here. At the end of the day, when the well is drilled, this is what we want to see on surface. This is the Christmas tree, the plumbing that shows that oil is going to go through the pipelines and to wherever we want to store them. Subsea, this is what you will see. This is the subsea Christmas tree, and there's going to be flow lines going all the way to the FPSO, or I mean a platform or jacket wherever we're going to be plumbing oil to. So this is the first phase. The first phase tells us that we acquire and we review data. So see this, our engineer here is acquiring a lot of data. Yes, a lot of data comes that sometimes it's going to take you weeks, months to read them and extract valuable information from. So data acquisition pretty much is the gathering of data and information from existing wells and making sure not just that that data is gathered, but that you take out relevant information from the data that you've gathered. And that leads us to the next step. So after you've gathered the data, you've taken out good information, you do an offset well review and go ahead to analyze all the things, all the probable things that can happen, all the possible things that can happen. Is it possible? Are there issues of stock pipe in that environment? In maybe 7 wells, you had stock pipe in 5 wells. That's very high probability. So what did they do in the other 2 wells that they didn't have stock pipe? You go there, you learn the lesson. Do they have wellbore stability issues? What did they do when they had those issues? How did they track the wellbore stability issues? Did they have severe losses? Where did they have these losses while they drill? Are we expected to have a geopressure environment? At what depth? Where does it start from? Is this environment a green environment? We've never drilled there before. We don't even know what the pressures are. How do we expect to get it? So this is all the questions we ask ourselves. And looking at the offset wells that were drilled there, we kind of analyze the data and get ourselves comfortable, get as much as we can get from it, and be able to build a case for ourselves and be able to build comfort for ourselves, putting all those details in the world that we're designing. Then the next step is after we've taken all that information, we go ahead to design the well. We got to throw out concepts. So looking out here, we have the base concept, option one, and this is just pretty much just an example. It's just throwing out our ideas on how the well can be designed. So here we have a base concept. We have an option one, option two, and option three. Now these wells, these 4 options we see here, go to the same reservoir. But if you look clearly, you see that they come with different designs. For example, the conductor goes to the same depth, the surface casing goes to the same depth. But if you look at the production casing for the first case, the first production casing goes below the first reservoir. Then we drill further, 8.5 inch section, then run a 7 inch liner. This is one concept. In this and the completions for that concept is going to be different. Perhaps here we might decide to run 4 3/4 screens, to perforate and run 4 3/4 screens, then run upper completions while we perforate this other reservoir in the 9 and 5/8 casing and run our completions here. So we have dual string completions here, but we have 2 different casing. So a casing and a liner. Here is a different strategy. Here we've decided to drill case off with 9 5/8 here, case off the first reservoir 9 5/8, then drill the next reservoir in 8.5, but perhaps run screens here and no need to set casing and cement. So this is another strategy, this is another concept. However, each one of them have their pros and cons. Perhaps there might be a very, very strong reason to want to run casing and cement, perhaps for hydraulic isolation. We don't want maybe gas, we maybe want to separate gas and water. We don't want gas to cusping, or we don't want water to coning. So we want to run that liner and cement it as required. In this section, in this particular concept, perhaps they've looked at it. There is no reason for us to want to do that. So yeah, we can get away with screens. Maybe it's looking at the reservoir, it's oil down to, so we have oil from top to bottom. In that case, you can run the screen. We're not bothered about gas or water coming in. So it depends on what we see, and that way we throw out all the scenarios out here, throwing out all the scenarios out here, and the team looks at it. We have the reservoir engineers, you have the geologists, you have everyone looking at it, and from here we now zone on a particular concept. Looking at the last two concepts, option two here is looks like option looks like option one was just a slimmer well bore. The issue with this one is that you don't have a you don't have a redundant hole. So in the case where you are drilling 8.5 here to run 7-inch casing from top to bottom, what if you lose this hole? You have to now drill 6-inch. Then after you drill 6-inch, and you're unable to get you sidetrack and drill 6-inch to the shallowest reservoir, what do you use to penetrate the next one? So then you are constrained. As a drill engineer, you should always try to have a contingent hole section in your pocket in the event that anything happens. The last whole section, this is pretty much, I would say the one I like. It's more optimized. Have your surface case, have your conductor casing, have your surface casing. It is possible to drill circa 6,000 to 7,000 feet from here all the way to bottom for this well that was designed. So this is pretty much what the concept selection looks like. So we look at it, we risk assess it, and we all agree that this is all one of these concepts is the way to go. Then after that is done, a concept is chosen, then we go into the main meat of it, which is the well design. So this is all the data that we need for well design. We need the surface and reservoir targets, we need the geological and seismic correlation. Is there shallow gas? Are we expecting shallow gas in that environment? Look at the pore pressure and fracture gradient data. Look at the reservoir composition. Is it sweet? Is it sour crude? We look at the temperature profile. Look at the lithological and petrophysical correlation. Site survey and bathymetry map if it's offshore. We look at the Christmas tree and completion status or type that we're going to be selecting. We look at pre-completion and completion requirements. The reservoir engineers have pretty much done the evaluations of the expected um, flow that they're expecting from that well. And it's based on that that the completion is designed. And so they've looked at the vertical lift performance, they look at the input performance relationship prior to choosing the completions equipment. And based on that completion equipment, we design the rest of the well. So let's not forget wells are designed from bottom to the top. So we look at the completion pressure testing requirements. We look at abandonment strategy. While we are thinking of how we're going to drill the well to execute for it to start producing hydrocarbons, we are thinking of how we're going to abandon the well, and with that comes where the top of cement will be ensuring that we seal off the necessary cap rocks while we're drilling these wells. We also look at intervention strategy in the event that we drill these wells. Sometime in the life of the well turns sick. Maybe there might be skin issues, or we might have water coming, we have gas coming. We might decide to go in and treat the well. We might decide to shut off water, or might decide to look for a way to shut off the gas or reperforate. Different things that we can do with the well. So the well design has to be able to accommodate every plan that we have in the future. So looking at it, this is some of the data I just spoke about. That's the looking at pore pressure, issues related to pore pressure. This probably defines it. So we have this is like an offset data. They perform the leak off test around here, formation integrity test around here. So what the pore pressure profile looks like. They use this mod to drill. This is what the lithology of that environment looks like. And with all this data, we use that to design our well. Then moving straight into well design. This is like the interesting part, guys. What are the things we look at when designing a well? Look at the rig sizing. Yes, when you're designing a well, you need to, when you do the preliminary design, you need to be sure that whatever rig you're selecting is able to drill this well. So they're going to be looking at what's the deepest depth that well, and what's the deepest depth the whole of those wells will go into. So when you look at that, when you look at the depth, you need to be sure that your rig can drill to that depth. Very important. What's the biggest casing you're running? So you look at all the casing size and the deepest depth you're going to. You need to be sure that your hoisting capacity can actually run the casing to bottom and actually lift it. You need to be sure that your hydraulic, the mud pumps you have on that rig, the hydraulics, that the rig is able to, that the rigs, the sorry, that the mud pump system is rated and good enough to be able to clean the hole as you drill. You need to look at the pipes that you have on the well. Do they have the torquing capacity, that the torque that you're going to have while drilling the well, and not when you're drilling the well, the pipe backs out. You're going to look at the rating of the pipes. You're going to look at how often those pipes are inspected, that you're not going to have a twist off in the well. So there will be a lot of things you'll be looking at in whatever rig you're selecting. Be sure that the rig the um has the capacity to be able to drill those wells. Then you look at the trajectory design, looking at your target, your surface location, and your target location to be sure that you're going to be able to drill this well without issues. You're looking at collision analysis. Collision analysis in the event that you have offset wells around there. Even when you don't have offset wells and it's a green field, when you are planning multiple wells from in that field, you have to plan those wells in such a way that the wells don't collide with each other sometime in the future. So you need to be able to account for all the wells that will be placed in that environment. And once you have them properly planned, you go ahead to execute. You don't have any issues. So all the wells should be able to have its place and not collide in the future. You're going to be designing your bottom hole assembly, and you're going to be and you're going to be analyzing them, ensuring that there are no that we're not going to have any um axial, torsional, and lateral vibrations, and in any way have any of those BHR, any of those bottom assemblies damaged. You're going to be looking at the torque and drag, ensuring that when you are drilling these wells, that the torque is not so excessive and you don't damage any of the drilling equipment or the drill string. And also, you're going to be looking at the drag, because when you have drag issues, it might even be possible to get the required weight that you need to get down to bottom and drill. And not just for drag while drilling, but also drag while running casing. I think we have that somewhere here. Yeah, casing drag analysis. You're going to also be looking at the bits, how you're going to be selecting them, casing seat selection, casing design, and kick tolerance. Kick tolerance, very important one. You want to be sure that in the event that you take a kick, you're able to circulate it out to surface without fracturing your last casing shoe. So all that will be calculated when selecting your casing seat. You're going to be looking at the casing drag analysis. That tells us the possibility of being able to get the casing on bottom. You're going to be looking at your drilling fluids and the hydraulics. So not, I mean, they're existing. We know that there are existing correlations that ensures that we're able to clean the hole. You have Robinson Steves, you have the Newtons, you have the Hershey Buckleys, a lot of them caissons. Whatever you're using, you need to be sure that it replicates what you're going to see. So you have to be able to use the particular correlation. There are a lot of them. There are a lot of them. Bingham plastic, but whatever you use, ensure that the ECD values it gives you and standpipe pressure values it gives you correlates, that you're using the right correlation, and you're not over predicting, make you to over choose equipment, and you're not under predicting, because it can come back and bite you. So your cementing design and hydraulics has to be spot on also, because if your cementing design is not proper, it's possible that while placing the cement, you can fracture the formation and you start to take losses. And once that happens, you're not going to be able to isolate your reservoir properly. Um, Not just cementing the reservoir or designing the slurry. There are various correlations also to evaluate your placement. You have the gas flow potential, pressure decay limit parameter. There are a lot of them to look at, that as you place this cement, that it properly isolates those zones without having gas inflow as the cement sets. You're going to be looking at the completions, you'll be looking at the well abandonment design. I spoke about that as you're designing the well, you're also thinking of abandonment. Then finally, you'll be looking at the cost. You probably the well should be properly. You should be able to properly cost these wells. And there are various places you can check. You can check with peers. You can go to database. There are large database where you can actually cross check if, or rather sense check if your cost makes sense. I mean, you have Rushmore reviews where you can go there quickly and check and see the typical well in your terrain, how much will it cost to drill that part, the type of well you're trying to drill. So this is just, I just put this on here to buttress collision issues as we're looking at here. Even though a sidetrack is planned, you can see that the wells are properly spaced to place into different reservoirs without having issues. So the well design process, which is the next step. So it's pretty much the same thing. Design. You are looking at the problem. What's in this case, our problem is what? Drilling a well, or rather designing a well that we want to drill. You brainstorm possible solutions. Look from, so from here to here, as far as I'm concerned, it's concept selection. So you are brainstorming possible solutions, you're researching ideas, you're establishing criteria and constraints, you're considering alternative solutions, and you are selecting, finally selecting an approach. So when you get to this gate, you have selected the type of well that you want to drill. Then moving up here, you develop a design proposal. That in from here, you're actually taking all the data that you need and you start designing the well. So you're making a model or prototype, you are testing and evaluating, and at this point, you are peer reviewing the design. And after that is done, you are refining the design, taking comments from the peer review to refine the design. Then finally, you are creating a solution, which is the well everyone has agreed that we're going to drill. Then finally, we are communicating the results by putting out a drilling program of how that well will be drilled. So this is just a quick summary. Since and at the end of the day, what comes out is the basis of design document. Then moving to the next stage, after that well is being designed, we go ahead to peer review. So we look at it, we look at the well, how has it been designed, what are the issues that can come out, has it been properly risk assessed, what are the problems that can come out. So everything is looked at in detail by experienced professional, keyword. And once that is done, everybody agrees that everything has been factored in, then we move on to the next stage. If there are any changes, they are made, and the next stage is the well programming. So the well programming is documenting sequence of steps to the guys who are going to be in the field of how this well will be programmed. Before I forget, let's not forget this phase of what I'm discussing pretty much has to do with well design. Let's not forget that there's a very, very clear path, or rather clear difference between well design and execution. So you guys always hear the drilling supervisor, the night drilling supervisor, and you hear the drilling engineer and senior drilling engineer. The, the drilling engineer and senior drilling engineer, they are guys who do the whole engineering, design the wells, ensure that the well is properly designed before they send the instructions or the drilling program to the guys who are going to be on the field drilling these wells. So it's like having an architect and civil engineer design a bridge or a house, then handing it over to the guys who are going to be in the field, who where you have an engineer supervising the job that's currently being done. So it's clear, design is done, the program or execution plan of how it's going to be done is written down properly and it's handed over to the guys. So I need us to get this clear difference between, they're all drilling engineers, but the drilling engineer I'm focusing on is the guys who pretty much do the design prior to going out to execute these wells. I'll be speaking about execution and drilling operations at some point. I'll be talking about different facets of operations, but let's have it in mind that the main part I'll be focusing on is with regards to design, because I think that's where most of the energy is spent. I'm not saying, please, I don't want to be misunderstood. I'm not saying that the guys who in the field don't pull their weight or don't have what, but they actually execute what is designed. Again, the focus is on the engineering part of it, as in guys who sit to design these worlds, and those are the condiments I'll be looking at. I'll be speaking about throughout this model. So in the well design, this is just showing steps in delivering the well. That here just showing that the casing that we're going to drill this hole, run this casing. So these are the details you're going to be seeing in the drilling program. And at the end of the day, you come out with something like this. This is just for display reasons. You come out with something like this. Sorry, for display purposes. You come out with something like this that documents that in here you have everything, all the procedures of how, I mean, all the procedures written in detail of how this well will be executed. Then, as that is done as well, we're also looking at different risks that can that we can have drilling these wells. So they are looked at in detail, and we look for mitigations to ensure that every risk is covered. And how is that done? So this is used to rank the risk. So here we see, here on the horizontal path, we see the likelihood, looking at, sorry, on the vertical part, look at the likelihood, that's the possibility of that risk happening. And we said, so there's a, here it's a greater than 90% chance that it will happen. That's almost possible that it will happen. That's happened in the industry. Here 50 to 90, here 10 to 50, here 3 to 10, and here less than 3% chance. So very not likely that it will happen. Here we have the consequences. Is it going to be insignificant? Is it going to be minor? Is it going to be moderate, major, or catastrophic? So where it is catastrophic and 90% chance of happening, you can see it's extreme. And it's possible that that project might be abandoned because of that thing happening, or possibility that we might lose 50% of our budget. We also consider that as extreme. So while we are looking at all, this is the way we rank the risks, all the way from very, very bad, sorry, very, very high to very, very low. And while we are doing, as we are doing that, we are also writing down the possibilities of, I mean, writing out the risk one by one. And as we are writing them out, we are ranking them. Sometimes after we've ranked them, we've put out the mitigation in place, we re-rank them. So when we re-rank them, if they come out green or yellow, okay, we know that it still exists, but we've been able to curb them reasonably. But whenever it comes out still red, we still look out for a way to further mitigate them, or we have our eyes on it throughout the project to be sure that it doesn't rear its head and bite us whenever we're not looking. So that's how this document is used. We write out all the risks, rank them from high to the ones that are really, really low. The ones that are very high, we look for ways to mitigate them significantly till they are green, or rather till they are acceptable. And when they're acceptable, it doesn't mean we take our eyes off them. We keep our eyes on them so that in case he rears his head, we already have ammunition, the right ammunition with us to be able to curb them. So that's pretty much how this document is. And once this is done, it's properly documented and it's called the risk register. So we can go up, we can always reference it, go up, pull up. Yeah, we knew this was going to happen. How did we plan to curb it? This is exactly what we're going to do, and we go ahead and solve the problem. Then finally, we drill the well on paper, where this is the conversation happening, guys brainstorming, getting solutions to problems, and on the field we have the pre-sport meeting. So you can see, look at these two pictures. The main difference between these two pictures that almost everybody in this picture are wearing hard hats, and that tells you that they're just pretty much getting off the rig floor. Well, everybody here is, I mean, are properly dressed. All these guys are in their coveralls and hard hats, telling you that, I mean, these guys are closer to the rig, or rather closer to the wellhead. So thank you very much, ladies and gentlemen. So the next series we'll be looking at all everything, most of the things we've highlighted here as per well design. We'll be looking at how the bits are selected. We'll be looking at how the trajectory is designed. We'll be looking at casing design. We'll be looking at kick tolerance. We'll be looking at how the casing seat is selected. We'll be looking at completions. We're looking at all the condiments of well design. This is pretty much why this model was designed. So this first video is just to talk in detail of how what the drill engineer does and how the well is designed. Thank you very much, everyone, for following to the end of the video. Thank you very much for listening. We'll see you in all the modules as we move ahead. Do not forget to share, like, and subscribe. See you on the next video. Bye for now.